Let us next start analysis 2 with metric spaces. In this video, we are going to see the definition of metric spaces and we will see some examples, not all of them right now itself. So let us start with the notion of convergence of a sequence of real numbers. So this is what the definition of convergence is. It is nothing new to us. We have already seen this many times. You have a sequence xn of real numbers and you have a real number x. We say that xn converges to x if for every epsilon greater than 0 there exists an integer n which is greater than or equal to that, the starting value of that index n, such that the absolute value of the difference xn minus x is less than or equal to epsilon for all integers, for all index values n greater than or equal to n. The meaning of this definition also we know very well, and that's not the point right now. Right now the point is this. You may remember that when we were studying the system of real numbers itself, when we were constructing that system, we defined the distance between two real numbers. In fact, we first did it for rational numbers and then only we constructed the system of real numbers and similarly did it there. And that is this definition. Say you have two real numbers x and y, then the distance between them is defined to equal the absolute value of the difference x minus y. Now this definition of convergence can be reformulated entirely in terms of this distance, like this next lemma says. So this is the lemma. We have a sequence xn of real numbers again, and we have a real number x. Then xn converges to x if and only if this sequence, the sequence of numbers d of xn comma x, that means the distances between the terms xn and x, these numbers also form a sequence if and only if this sequence converges to 0. And it makes sense also because convergence means the xn's are getting closer and closer to x. So the distance between the terms and x should vanish. And the proof actually is almost trivial. I will just give you the hint in which everything is there to write a proof. The hint is this. Note that this is less than or equal to epsilon, not really writing for which n or what epsilon is. You know in what sense I am considering this inequality. If and only if this. It's easy to see that this is nothing but this ultimately. And this then is the distance between xn and x. Okay, and this much is enough to tell you, if you do not have any doubt with these things, about these things, that these two things are equivalent. Alright, so that lemma tells us that we can formulate the notion of convergence entirely in terms of distance. Fine, so what's the big deal? We haven't actually done anything new by doing it, by reformulating convergence in terms of distance. So what's the point of doing this? See, the thing is this. We have already gone through many things in analysis 1, and by now we know very well how important convergence is, how important the notion of convergence of sequences is. So we do not really want to be able to do this only with sequences of real numbers. We want the similar notion to also be available for other types of mathematical objects like sequences of complex numbers, sequences of vectors, matrices, functions, and even sequences of sequences. How can we do this? There are two ways of doing this. One leads us to the notion of topological spaces, which we won't see right now. Okay. Actually, we are doing topologies separately, but that's a different matter. The other notion leads us to the idea of metric spaces, and that's what we are trying to do. So, our starting point is the observation that convergence can be reformulated or expressed entirely in terms of distance. So, to do that similar thing for other types of mathematical objects, we now need a notion of distance between them. Say, we want to be able to say what the distance is between two complex numbers, which won't really be very difficult or different than what we already have for real numbers, because you can follow the almost identical definition for complex numbers. If z and w are two complex numbers, then you define the distance between them to be the absolute value of z minus w. Okay, so that will give you a notion of distance. But you cannot really do this for other types of mathematical objects. Say you consider the distance between two vectors. You can consider the difference of two vectors of the same size, but then absolute value, there is no absolute value of vectors. For complex numbers we have absolute value, but for vectors we don't exactly have absolute value, we have something else. Fine, say you use that to define distance between vectors, but then what will you do for matrices? Again, you can take difference, but then you get stuck. For functions, for sequences, so this makes you realize that it's a little cumbersome to keep defining new notions of distance whenever you encounter a new type of mathematical object. Today you have these things, tomorrow say something else becomes important, and there also you somehow need to consider the notion of convergence of a sequence whose terms are that new type of mathematical object. What will you do then? Will you again define another type of distance? Instead of that, what we can do is that we can define distance more generally. So what the mathematicians did, they considered the most important properties of the distance function that we already have between real numbers, and they took those properties as the starting point of a general definition of distance, and these general functions are called metrics. And a set on which you have this general function which helps you measure the distance between two elements of the set, they are called metric spaces. That's what it is, that's the idea. But what are those most important properties that ordinary distance has? Let's see next the definition of metric spaces. In that itself we will have those general properties. So this is the definition of a metric space. A metric space is a pair, an ordered pair like this, x comma d, of two objects x and d, where x is a set and d is a function like this. The domain of d is the Cartesian product of x with itself, x times x, and the range of d is the set of all non-negative real numbers. And there are some properties or some conditions that the function d satisfies, and these are the conditions, there are 4 of them, which are those important properties that the distance between real numbers has, that function has. And these conditions or these properties are very natural, which we expect a distance function to have. The first condition is this: for any element x in X, d of x comma x is equal to 0, which is something natural because we want the distance of an element from itself to be 0. We do not want that to be positive. And next comes positivity. If we consider two distinct elements of x, say x and y are different elements of x, then we expect the distance between them to be positive. We do not want two distinct elements to have 0 distance between them. And in this whole context, the d values are considered to be distance between those two elements which are put here in the d function. Then we have symmetry. For any two elements x and y, distinct or not distinct, that does not matter. The d value of x comma y should be equal to the d value of y comma x. How the distance between two elements is measured should not depend on the order in which they are arranged. The distance from this place to that place should be the same as the distance from that place to this place. So this is symmetry. Okay, so you can see how natural these properties are. And there is that fourth one, which is triangle inequality. Let me write that on that side. The triangle inequality states that for 3 points x, y and z, I should perhaps say 3 elements. For 3 elements x, y and z in X, which are not necessarily distinct, 2 of them may be the same, in fact all of them may be the same, but for them we have this inequality. You are already familiar with this from our usual triangle inequality for distance between two real numbers. So that property also has been kept. Although these first 3 properties are very important, but this fourth one is what gets things done in terms of calculations. And in this context, the elements of x are called points, okay, and the function d is called a distance function or a metric on X. So that is the notion of a metric space. It's a pair of 2 objects, one of them is a set and the other one is a metric, which is a particular type of function, and it is interpreted as measuring distance between 2 elements of that set X. The way this definition has been written, it's not exactly the only way. Elsewhere in other texts, you will see a slightly different way of writing that same definition, which you can see from this next remark. The conditions A and B, the first condition and positivity, these 2 conditions can be combined and we can give a single condition in place of them, which is this. For any 2 points x and y in X, the distance between them is 0 if and only if they are the same point. Going back to the original definition and seeing this condition, it's a very trivial exercise to see why those 2 are equivalent to this single one. Next we come to the first example, which is not surprising considering the source of our definition. The set of real numbers forms a metric space with that distance function, which is given by the absolute value of the difference between 2 real numbers. So formally if we define it, looks like this. So d is the function from r times r to the set of all non-negative real numbers, and the definition is same, and the fact it is already there, actually it's already there, all the parts to show that this is a metric space have already been done in analysis 1, but nevertheless it's exercise 2. So when we will solve this exercise, then we will just simply say where to go back and look for those parts that will tell us that together that this is a metric space. Now, this metric is called the standard metric on R, this specific D, and if we simply say that R is a metric space without saying explicitly what the metric is, it is to be understood that the metric is D unless specified otherwise, because there are other metrics also on R. Another important metric, it's going to come, okay, it's called the discrete metric. So that is the first example, which is nothing new. Example is that of induced metric spaces. Say you have, this is a little general. Say you have a metric space x comma d and you have a subset y of x. Then we can restrict the metric, the function d, which originally has the domain x times x, to its subset y times y, because y is a subset of x, so y times y is a subset of x times x. So d can be restricted to this subset to get this restriction. Then the fact is that this restriction is a metric on y, which we are going to prove in the fourth exercise of this section. And that makes this pair, whose first part is y and the second part is this restriction, a metric space itself. This metric is called the metric induced by D on y, and this metric space is called the subspace of the original space x induced by the subset y. Okay, so this way, if a metric space is given, actually any subset forms a subspace, and so in that way we get other metric spaces. For example, if you take the real line, that is the usual set of real numbers with the standard metric, then any subset on it forms a subspace. That subset can be an interval, a closed interval, or it can be any other familiar sets. For example, the set of natural numbers, the set of integers, in fact the set of rational numbers. If you consider the subset of rational numbers, you get the metric space of rational numbers. Okay, and which is in fact the first thing we did when we were constructing the system of real numbers. Gradually we did this now. So before getting to the metric space of real numbers, we got to the metric space of rational numbers. Okay, so we can have that, in the other direction also. From the real numbers, we can go to the subspace of rational numbers. Say n is a positive natural number, a positive integer. We already know what Rn is. Rn is the Cartesian product of n copies of the set of real numbers R, and the elements are n tuples, ordered n tuples, where the coordinates or components are real numbers. So this, we are familiar with this. Now on this set we define a distance function. So, and we call it d little l2. Okay, there is a big L2 also. D little l2 is a function from Rn times Rn into the set of non-negative real numbers, and this is the definition. You are actually familiar with this distance function from analytic geometry, coordinate geometry. In fact, you got this in school. So what this does is that it takes two such points and it considers the difference between corresponding coordinates, squares them, adds those squares, and then takes the square root of that sum. That is the distance, which if you express more compactly, it looks like the square root of this sum. So in fact, this example is given by the author, which is the distance by this function between these 2 points in the two-dimensional plane whose coordinates are 1 and 6, and for the second one they are 4 and 2. So if you calculate the differences, the difference between 1 and 4 is minus 3. So minus 3 square, you can put 3 square, and the difference between 6 and 2 is 4. So 3 square plus 4 square is 25, its square root is 5. So 5 is the distance. And it turns out that yes, this really is a metric on Rn, and as such this pair is a metric space. It's called the Euclidean space of dimension n. You do understand that we are not looking at a single metric space here. As you change n, you keep getting new and new spaces. So this is the example for n equal to 2. And the fact that this is a metric space will be proved in exercise 6. Again have the same set Rn for a positive integer n, but this time the distance function is different and we call it d little l1, and the definition is also different. Instead of considering square root of sum of squares, what we do here, we consider the absolute value of the differences of corresponding coordinates and add them up. That's it. That is what this distance function gives us. This ordinary sum, no square root, no square. So in this, if our n is 2 and say we take those 2 points 1,6 and 4,2, then the distance that this function measures between them is 7. Okay, so you can see that it is more than the previous one, which was 5. Actually there is a relationship. Oh, by the way, before I get to that, it turns out that this is also a metric on Rn. So although Rn is simply Rn, but we now have two metrics, the Euclidean metric and this one is called taxi cab metric. You can see the text for why it is called so. Now there is a relationship between these two metrics, which is given by this next inequalities. The fact that this 7 is greater than that 5 value can be seen more generally here. The distance that dl1 measures between 2 points in Rn is at least as large as the distance that dl2 measures between those 2 points. And in turn, this dl1 distance is less than or equal to square root of n times dl2 distance. In exercise 7, I think we are going to prove that this is a metric space, and in exercise 8 we will prove these inequalities. So with that, let me just end this video here itself. There are other examples which we will discuss in the next video. So that will be all for tonight. So see you tomorrow with a new upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.